In the previous video, we talked about continuous random variables. Specifically, we defined a random variable x with the CDF fx of x to be continuous if its CDF is a continuous function. And we talked about the fact that the probability mass function is not well defined for continuous random variables. And the reason for that was this. Probability mass function, by definition, is the probability that x equals u for any u. And for continuous random variables, we saw that probability that x equals u is going to be 0 for all u's. So if I want to have a probability mass function for a continuous random variable, it's just going to be a 0 function. So we want to kind of solve this problem in this video. We want to introduce a new concept, which is probability density function. It's very similar to probability mass function, but it can be defined for continuous random variables. So let's review the example that we saw last time. It was a simple example, our first example of a continuous random variable. And the example was this. We chose a random number, uniformly at random, in the interval from a to b. So basically that's my random variable x. And we specifically said that it's x is chosen uniformly from a to b, which means that probability that x belongs to any interval x1 to x2, so probability that x is between x1 and x2 is going to be the length of the interval from x1 to x2, so x2 minus x1, divided by the total length of this line segment from b to a, so from a to b, so over b minus a. Of course, this is true for x1 larger than a, less than x2, less than b. And we found the CDF for this random variable. The CDF, I have shown it here. It's 0 for values less than a. It increases linearly to 1 and then it stays at 1 after x equals b. So we said that this is a continuous function, and that's why we said that this random variable x is a continuous random variable. So there is no jump in the CDF. Now, in this video, we want to talk about probability density function for continuous random variables. So consider a continuous random variable x, and we know that probability that x equals u is going to be 0 for any u. So this is 0, but we can look at the probability that x is, let's say, larger than u and less than or equal to u plus delta. This probability can be non-zero. So, but this probability goes to 0 as delta goes to 0. So if delta becomes a very small value, then this probability becomes smaller and smaller and goes to 0. So what we do here, we divide this probability by delta and look at this limit as delta goes to 0. So basically what I'm doing here is that I'm choosing a value u, and then I'm looking at u plus delta. I am looking at the probability that x is in this interval and divide that probability by the length of that interval. That's why we call this probability density. So it's the density of the probability. It's the probability divided by the length. So it's probability per unit length. So this limit, if it exists, I call it f of u. And we have a subscript here, fx of u, which means that this is the PDF for the random variable x. Okay, so that's the concept of a PDF. So let me write it down again here. So I define fx of u, which is the PDF for the random variable x, as the limit as delta goes to 0, probability that x is larger than u, less than or equal to u plus delta, divided by delta. Now we know that the probability that x is between u and u plus delta is basically f, the CDF at point u plus delta minus the CDF at point u. It's just the result of the definition of the CDF. So let's write this as limit as delta goes to 0, fx of u plus delta minus fx of u divided by delta. Now if you look at this from calculus, we see that this is in fact the definition of this limit is the definition of the derivative of the CDF. So this is in fact is equal to the derivative of the CDF at point U. Of course, if the CDF is differentiable at that point. So the PDF is in fact the derivative of the CDF. So fx of u, which we define as the probability density function for random variable x, is the derivative of the CDF. And we can provide this as a definition for the PDF. So consider a continuous random variable x with CDF fx of x. Then we define the PDF of x as the derivative of the CDF. So before discussing this further, let's quickly find the PDF for our random variable x that we discussed here. So we have the CDF, and we want to find the PDF. Well, we can quickly take the derivative fx of so basically the CDF fx of x is going to be constant for values larger than b, and it's going to be constant for values less than a. So it's going to basically, if I take the derivative of this, fx of x is the derivative of the CDF, is going to be 0 for values of x that are larger than b or less than a. So that's the property of a derivative. If I have a constant function, its derivative is going to be 0. Now for values between a and b, or let's write it as between a and b, then the PDF is just a derivative of a linear function, x minus a divided by b minus a, and is the derivative of x minus a, b minus a is just going to be 1 over b minus a. Okay, so if I want to plot this, what do I get? If this is x, this is a, this is b, the PDF is going to be 1 over b minus a from a to b, and it's going to be 0 for all other values. So this is the PDF of my random variable x here. And it's kind of what we expect, right? If you think about it, we chose the random variable uniformly from a to b. So it's the PDF is constant from a to b. And it's going to be 0 outside of this interval because x, this is the kind of the domain, this is the range of my random variable a to b. So the PDF is 0 outside of this interval. Okay, so that's just an example of a PDF. And as we said, that this is our definition of the PDF. It's just a derivative of the cumulative distribution function. But what it means intuitively, if we look at the definition that we had here, we define fx of any value u or x as the limit as delta goes to 0, probability that x larger than u less than u plus delta divided by delta. So if you choose a small delta, we can say that fx of u, the PDF, is approximately probability that x is less than u plus delta and larger than u divided by delta. In other words, if I want to find the probability that x belongs to the very small interval from u to u plus delta, I can look at this probability density function and multiply it by the length of the interval. And again, this is consistent with our intuition that the probability density function is the density of the probability. To find the probability, we look at the length of the interval multiplied by the density of the probability. Of course, this is only true for small delta, so I should replace this equal to with this is approximately equal. So from here we can kind of talk about properties of the PDF. Remember, PDF fx of x is the derivative of the CDF. So from calculus we conclude that CDF is obtained by integrating the probability density function. So basically it's integral from minus infinity to x fx of u du. So that's one property. So if I have a CDF, I can take its derivative to obtain PDF. If I have a PDF, I can integrate it to obtain the CDF. Now remember that probability that x is between a and b is given by definition is again fx of b minus fx of a. That was the property of the CDF that we saw previously. If you replace the CDF by the integral of the PDF, you obtain integral from infinity to b fx of u du minus integral from minus infinity to a fx of u du, and again from calculus we conclude that this is the integral from a to b fx of u du. So if I ask you what's the probability that x belongs to this interval, you can find that probability using the probability density function. You can, if you have the CDF, you can directly use this, or you can find it from the PDF. You should get the same result. And note that in discrete random variables, when we're talking about discrete random variables, I was very careful when I write x larger than a or x less than or equal to b. Here, it doesn't matter because x is continuous. So probability that x exactly equal to a is going to be 0 is equal to probability that x is equal to b. So in fact, if I ask you what is for a continuous random variable, what is probability that x is less than b and larger than a, is going to be the same value. Okay, so let me summarize properties of the PDF. So PDF is always positive. Remember, it was the limit of the probability that x is between x and x plus delta divided by delta. So delta is positive, probability is also positive. So this kind of limit is also going to be positive. It can be 0 at some points, but it cannot be negative. So that's the first property. Now, if I integrate from minus infinity to plus infinity, what do I get? If I integrate over all values, right, I should get 1, because based on what we just discussed, this is the probability that x is larger than minus infinity and less than plus infinity. So that's going to be 1. That's the second property. And that's the property that we just discussed. Probability that x is between a and b is fx of b minus fx of a, which is equal to integral from a to b fx of u du. And finally, if I give you a general set, I give you what is the probability that x belongs to set a. A could be union of some intervals. Then you integrate over that set a, and you will obtain the probability. Okay, so I have provided a lot of formulas. So let's look at an example to make sure that we can practice with these formulas, and we can use PDF to find probabilities. Okay, so here's an example. Let x be a continuous random variable with the following probability density function. So the PDF is given. If you want to plot it, fx of x. So if I put x equals 0, it becomes e to the minus 0 is 0. So it becomes c. C here is a constant. It's a positive constant. And then it decreases exponentially as x becomes larger and larger. So my question for you is first to find c, and then find the CDF of my random variable x here, and then find the probability that x is between 1 and 3. So I suggest that you solve this problem before watching the rest of the video. Okay, let's look at the solution. First of all, we need to find c. You can find c by using this property that the integral from minus infinity to plus infinity fx of x dx must be equal to 1. If I want to show it in the figure, what it says is that the integral, or the area under this curve, from minus infinity to plus infinity must be 0. Sorry, must be equal to 1. Okay, so let's find this area. The PDF here is going to be 0 for negative values. So integral goes from 0 to infinity, c e to the minus x dx. And from the table of the integrals, we find that the integral of e to the minus x is just minus e to the minus x. So going from 0 to infinity, we obtain, c comes out, it becomes e to the power of 0 minus e to the minus infinity. We obtain c. This is 1, this is 0, so times 1. So the whole thing must be equal to 1. So c must be equal to 1. Okay, so that's part A. We want to find the CDF. How do you find the CDF? We have the PDF. We just integrate it to find the CDF. So fx at any point x is equal to integral from minus infinity to x fx u du. Okay, so this is gonna be, again, first of all, this is gonna be 0 if x is a negative value, because PDF is gonna be 0 for negative values. So for x larger than 0, then fx of x is gonna be integral from 0 to x fx of u du becomes integral from 0 to x. The PDF for that point is c e to the minus u du, but we found that c equals to 1, so it's just equal to this. And this integral, again, is just the integral of e to the minus u, which is going to be e to the minus u from 0 to x. And this becomes 1 minus e to the minus x. So if I want to summarize, the CDF fx of x is going to be 1 minus e to the minus x for positive values of x and 0 otherwise. So that's the CDF for this random variable. And the last part, we need to find probability that x is between 1 and 3. So probability that x is between, it doesn't matter if I put less than or equal to, so because this is a continuous random variable. So we can find it in two ways. One way is to just directly use the CDF, so fx of 3 minus fx of 1. And we found the CDF here is just 1 minus e to the minus 3 minus 1 minus e to the minus 1, which becomes e to the minus 1 minus e to the minus 3. Another way is to write this as integral from 1 to 3 fx of x dx. Right? We can find the probability using the PDF as well. It's integral from 1 to 3. This PDF, we found this is going to be just c equals 1 e to the minus x. So e to the minus x dx. And again, if we find this integral, this is going to be equal to e to the minus 1 minus e to the minus 3. So we get the same answer. If I want to show it in the figure, basically that was the PDF. And to find the probability that x is between 1 and 3, what we do is that we find the area under the PDF from 1 to 3. Okay, thank you.